Welcome to AP Chemistry. We begin our discussion of equilibria, building upon our understanding of chemical kinetics. All equilibrial systems that we will work with are reactions that occur in one elementary step, i.e. a single collision. It should be intuitive from our discussion of vapor pressure, that also involved a certain equilibrium pressure, that the forward and reverse processes will occur at a given temperature until the speed of both processes become exactly the same. This means that although at the micro level change is constantly occurring, at the macro level no change is evident. The system is thus naturally driven to this equilibrium point, or lowest change in free energy for our system. To represent this point of equilibrium, we can set both the rate law of the forward and reverse reactions equal to each other, and, rearranging, we can have a ratio of rate constants, as well as a ratio of products to reactants at equilibrium. Both of these ratios, at a specific temperature, are equal to the equilibrium constant K. Let us take the same reaction system below at a constant given temperature. It doesn't matter what the system begins with. Over time, the ratio of products to reactants will shift to become a constant value at a given temperature. Therefore, if the system becomes disturbed in some way, say by adding more reactants or more products, or by removing reactants or removing products, then the system will shift in a way to reduce the effects of that stress and thus recreate the same constant value at a given temperature. These equilibrium shifts also occur with changes in temperature. Now, you should recall that higher temperatures will always produce higher vapor pressures, see the equation provided, and higher temperatures will always result in a higher value for a reaction constant, again, see the equation provided. But there is a key difference for the equilibrium constant K. This is because equilibrium is effectively a competition in favorability between the forward and the reverse reactions at a given temperature. Thus, if delta H, our enthalpy value, is positive or endothermic, a higher temperature will result in a larger equilibrium constant. However, if our enthalpy value is negative, that is an exothermic process, a higher temperature will actually result in a smaller equilibrium constant. Now, let's understand why. Note the reaction diagram provided. The forward process is exothermic, but the reverse process is endothermic. At higher temperatures, the reverse process will become more favored, since it requires energy to occur, while at lower temperatures, the reverse process will become less favored. Thus, at higher temperatures for this reaction system, the K value will be smaller. But at lower temperatures, where the reverse reaction is not as favored, the K value will be larger. Note how the dynamics change if the forward process is endothermic. At higher temperatures, the forward process will become more favored, since it requires energy to occur, while at lower temperatures, the forward process will become less favored. Thus, at higher temperatures, for this reaction system, the K value will be larger, but at lower temperatures, where the forward reaction is not as favored, the K value will be smaller. Finally, equilibrium shifts also occur in reference to changes in volume, if that change in volume results in a disproportionate change in the concentration of either the reactants or the products. For this reaction system, the total moles of gas on the reactant side is not equivalent to the total moles of gas on the product side. Therefore, any change in the volume will affect either the forward or reverse reaction more than the other. In this case, at smaller volumes, the reverse reaction will become substantially more favored, since two particles are required for a successful collision to occur. Thus, the syringe at first shows the old equilibrium position. Then, the syringe volume suddenly decreases, which increases the concentration of the nitrogen dioxide. Then, finally, the system shifts to favor more reverse reactions in order to restore the equilibrium. What is important to note is that equilibrium positions are manifold, but the equilibrium constant will be the same at a given temperature. We can also note here that solid and liquid states will never affect the equilibrium constant. This is because the concentration of a solid, or the concentration of a liquid, is always constant due to having a definite density, and therefore changes in amount or in volume will never affect the equilibrium. Thus, the equilibrium expression is not dependent upon either solids or liquids. Provided is a chart of all the possible changes that an equilibrium system can undergo. Take a moment to read through and rationalize the general patterns in these 14 different scenarios. Although numerous, if we understand changes in temperature and volume as having a similar effect to changes in the amount of reactants or products, these shifts actually become much more easy to rationalize. Take a moment to predict the shifts that might occur in this particular reaction system. Now let us analyze another reaction system. In the table below, percentages of ammonia are provided at different equilibrium conditions. Notice how at higher pressures, ammonia becomes more favored. This is because the reaction has 4 moles of gas on the reactant side and 2 moles of gas on the product side. Therefore, the reaction will shift to favor the production of more ammonia at higher pressures. However, notice how ammonia is also changing in relation to temperature. At higher temperatures, ammonia is becoming less favored. Therefore, this reaction must be an exothermic process. It is convenient to think of heat as overall an either reactant or product, and in this case, our overall reactant in the reverse process. Therefore, the reverse process will be favored at higher temperatures, and ammonia will become less. It is also important to note how thermodynamics and equilibria converge here. When we solved for the change in G for a particular process, we understood that the thermodynamics of certain processes were temperature dependent. In this case, since the enthalpy value and the entropy value are both negative, change in G will be negative or spontaneous at low temperatures. Notice that using equilibria, we are effectively saying the same thing, only now in reference to which reaction, either the forward or reverse, will be favored. Therefore, in this case, the forward reaction will be favored only at low temperatures. Remember, this should not be confused with the kinetics or speed of a given process, for at 25 degrees Celsius, the forward process of this reaction is not observable due to the fact that it is simply too slow to occur at any noticeable level at this temperature. Now note the diagram for this particular reaction on the industrial scale. Catalyst beds and temperatures of around 400 degrees Celsius are used for kinetic reasons within the reactor. However, N2 and H2 is constantly injected at high pressures and recycled into the reactor at high pressures in order to shift the equilibria to the right as much as possible. The heat exchanger is present to conserve the heat given off by the reaction and to recycle it with the unreacted N2 and H2, while the condenser is constantly removing the NH3 that has been produced. This process, the Haber process, which effectively manipulates both kinetic and thermodynamic conditions to generate as much ammonia as possible, is the fundamental reason why the production of cheap and accessible fertilizer has exploded to feed the world. In this reaction system, however, with a positive enthalpy value and a negative entropy value, has a positive value for change in standard G at all temperatures. Nevertheless, it is still possible to manipulate this reaction on the industrial scale using the knowledge of equilibria. To recapitulate, there can be only one equilibrium constant for a particular reaction system at a given temperature. However, the number of equilibrium positions that can express this equilibrium constant is effectively infinite. Drawing upon the law of mass action, which we have already discussed at the beginning of this video, we can represent the equilibrium expression for any given reaction. If the factor of a given reaction is altered in any way, the new equilibrium constant must be equal to the old equilibrium constant raised to the power of that factor. This can easily be seen by comparing the expressions provided below to each other. Furthermore, although equilibrium constants are typically given in concentration, they can also be given provided with pressure. However, although they are both constant for a given system at a given temperature, they are not necessarily the same value, since pressure, of course, is not equal to concentration. Pressure is equal to concentration times RT. If we substitute in for pressure the equivalent concentration, we can derive a relationship that relates Kp to Kc, just as pressure relates to concentration. That is, Kp is equal to Kc times RT raised to the power of the difference in moles of gas particles in a given reaction. Now, although you are required to be very familiar with equilibrium shifts conceptually, you will also be required to calculate whether an equilibrium shift will occur. This is because in many given scenarios, it will not be clear which way the reaction may shift from the given conditions. Take, for instance, a reaction given at equilibrium in the section above. If we substitute the values into the equilibrium expression, we can find the equilibrium constant at a certain temperature. Of course, we know what would occur if more nitrogen, a reactant, was added to this system. It would shift to the right to produce more products. However, what if we didn't know more nitrogen was added to the system? What if the values were such that we could not easily tell what might occur? We can then calculate a reaction quotient Q. This is simply a value that we can use to compare to the equilibrium constant K. If Q is found to be less than K, the reaction will shift right. If Q is found to be greater than K, the reaction will shift left. If Q is found to be equal to K, then the reaction system is at equilibrium and no shifts will occur. Since in this case Q is calculated to be less than K, the reaction shifts right to create a new equilibrium position. In a separate video dedicated only to solving equilibrium problems, we will work with how we can predict the resulting concentrations of any equilibrium system. Till next time when we consider the mysteries of the absolute, Crip.